Alright, so in this video I'm going to introduce some new concepts which will enable us to be able to do pipe and plumbing problems. So the first concept I need to introduce is just laminar flow. So laminar flow is it's represented by this top picture here in a pipe, and it's a very smooth flow. It's easily characterized by like this nice smooth parabola. And then turbulent flow is a very rough flow. You can see that there's these eddies and just general turbulence affecting the flow, so it's very rough flow. And the way that we characterize laminar or turbulent flow mathematically is with the Reynolds number. So the Reynolds number is defined as the ratio of inertial forces to viscous forces. And for flow in a pipe, we say that the Reynolds number is equal to the fluid density multiplied by the average velocity multiplied by the pipe diameter divided by the fluid viscosity. And then generally we say that when a Reynolds number is less than 2000, that characterizes laminar flow. You're in the laminar flow regime if your Reynolds number is less than 2000. And if your Reynolds number is greater than 4000, you're in the turbulent regime. In between 2000 and 4000, you're in the transition region. And flow in the transition region is very hard to characterize mathematically. It's hard to determine pumping power or pressure drop. So whenever you're designing a system, you typically want to design it so that your flow is either in the laminar regime or the turbulent regime, and you just want to completely try to bypass any flow regimes that would be in the transition region. So the next concept to introduce would be shear stress. So if you look down in this picture down here, this is a laminar flow through a pipe, and we see shear stress tau sub W right here. So the way to think about shear stress as it's a flux of momentum. So if we look right here, this is the wall of the pipe, and at the wall of the pipe you would imagine that there's zero velocity of the fluid, right? Because there's no flow there, it's a solid. And then right next to the wall of the pipe, that's where you're going to have the greatest frictional effects. So the wall is going to have a frictional effect, and it's going to retard the motion of any of the fluid that's moving right next to the wall. And then that fluid that's slowed down by the wall, it's going to slow down all the fluid that's moving next to it. And then the fluid that's moving next to it is going to slow down the fluid that's moving slightly below it in this picture, and so on and so on. So you have this flux of momentum in the y direction, or in the radial direction in this case. So that's the way to think about shear stress. And then over here you can see a laminar velocity profile. It's just a nice smooth parabola. And then in the center you see that you have the max velocity in the center. And just a neat little identity here is that the average velocity, u mean, is equal to 1/2 u max. So typically we're most interested in the average velocity, u mean, and that's the average velocity is the velocity that you'll see in the Reynolds number definition. A lot of the times you might see that this is how they write average velocity. In my videos I'm just going to say u is the average velocity, and if I need to talk about u max, I'll write u max out. Okay, so that pretty much does it for the introductory concepts. The next thing that I'm going to do is just derive an expression for shear stress in a pipe, and then I'll go on from there to just manipulate mechanical energy balances into some more useful forms. And then in the next video I will start using all the derivations that we perform in this video to start solving actual problems. So just give me 1 second, I'll come back with a setup for a derivation of shear stress. Okay, so now we're going to derive that expression for shear stress in a pipe. So if you look at my drawing of a cylinder here, this is just going to be one differential unit, and then we're going to characterize it with length L. And then we have flow, and so the flow is coming from this direction, and it's going to flow through the pipe and just keep flowing. So this is just one small section of a pipe. You can imagine that this is just normal flow inside the pipe. So you're going to have the flow inside the pipe is going to be pushing on this side of our differential cylinder here. So this is going to be, we'll call it P1. And then on this side, we'll have pressure acting in the opposite direction. We'll call this our P2. Alright, and then at the wall, you'll have shear stress, and it's going to be retarding the flow. It's going to be acting in the opposite direction of the flow. So we're going to have shear stress acting in this direction. And that's tau sub W. Okay, and then this is our coordinate axes. So we have in the straight up direction is the radial direction, and then along the pipe is in the z direction. And then the next thing that I want to do is just define P2 in terms of P1 using a Taylor series expansion. So we can say that P2 is equal to P1 plus our time step or spatial step L times the first derivative, so dP1 dz. And then we just want to do a force balance on this, so we're going to say that F is equal to mass times acceleration. So we have our pressure force acting on the left hand side here, so that's P1 times the cross-sectional area, which is just, I'm going to do A sub C, and then we're going to subtract from that the P2 times the cross-sectional area, but I'm going to sub in our Taylor series expansion definition, so minus P1 plus L times dP1 dz, and multiply that by the cross-sectional area. And then we have our shear stress, and the shear stress is acting along the entire surface area, so the entire surface area, so we're going to multiply our shear stress by the surface area. So we have tau sub W times A sub S for surface area. And then I'm just going to treat our frame of reference as if it's stationary, so we're going to say that mass times acceleration is equal to 0. Alright, and then what we can do is we can just start subbing in relationships for the cross-sectional area and the surface area for a pipe. So in a pipe, the cross-sectional area is just going to be pi r squared, and the surface area will be the circumference 2 pi r times the length L. Okay, then we can see that this term right here will cancel this term. Let's go ahead and rewrite this now, so we can say that a negative L times dP, I'm dropping the sub 1, so dP to z times pi r squared is equal to a tau sub W times 2 pi r L. We can see that the pi's will cancel, the L's will cancel, and this r will cancel with one of these r's here, and then we'll end up with this expression here for the shear stress in a pipe. So tau sub W is equal to the radius divided by 2 times the quantity of this differential here. So the pressure changed with in the z direction. Okay, so that is just the derivation of an expression for the shear stress in a pipe. And then from that, I'm going to move on to probably a more useful derivation where we start dealing with the mechanical energy balance and start getting things in nice, easy to solve formats. So just give me 1 second and I'll be back with the setup for that. Okay, so what we're looking at here is just a pipe, and it's elevated or it's slanted. So this is a pipe and it's going to have some angle theta here. So we'll call this angle theta. And it's going to be, so this is our axis. I have the radial direction defined like this, and the z direction defined along this. So if we're interested in the elevation between here and here, we just think of it as a triangle, and we want, so we'll call this L. This is the length of our pipe. So if we wanted the vertical distance, we would just do some trig and say that this is L sine theta. So that's our change in the vertical direction. And then we're going to have flow coming from the bottom and going up the pipe. So we'll have a pressure acting in this direction. So that's our P1. And then we'll have a pressure acting in this direction. And that's our P2. And then again, we'll have a shear stress acting on the wall. Redo that one. Okay, so that's our tau sub W. And again, the flow is going up, so I'll just draw a velocity. So that's our velocity. It's going up. The way that this is different than our last derivation is that we have the effect of gravity now. So we're no longer horizontal. We have gravity acting on our fluid. So if we look at like a point or a force diagram, we have gravity acting straight down. So that will be our g sine theta. And then we have a pressure acting up like that. It'll be P1 times the cross-sectional area. And we have pressure acting down. So that will be our P2 times the cross-sectional area. Then we have a shear stress acting in this direction. So that will be our tau sub W times the surface area. So this would be our force diagram. Again, we want to just do a Taylor series expansion to define P2 in terms of P1. So we'll have P2 is equal to P1 plus L dP1 dz. Alright, and then again, we just want to do a force balance. F is equal to ma. So I'm going to drop the sub 1 from our pressure. So I'm just going to say P AC minus the quantity of P plus L times dP to z times the cross-sectional area minus tau sub W times the surface area. And then now we're going to add our gravitational force here. Let's see, so that's going to be the way that I'm thinking about this is that force is equal to a mass times acceleration. Our gravitational constant is an acceleration, so we need a mass. So a mass is going to be our fluid density multiplied by the volume. So we're going to have rho times the cross-sectional area times the length, and then multiply it by our g sine theta. And then again, we're just going to have a still frame of reference, no acceleration. So it's going to be equal to 0. Okay, and then again, we're just going to be talking about a pipe here. So for a pipe, we know cross-sectional area is going to be pi d squared on 4, and the surface area is equal to pi dl. And then let's just start simplifying. So we know that this term will cancel with this term. Then I get a negative L times dP dz times the quantity of pi d squared on 4. And I'm going to subtract from that shear stress multiplied by the surface area, which is pi dl. And I'm going to subtract from that the fluid density multiplied by the cross-sectional area, So another pi d squared over 4 times the length g sine theta equal to 0. Okay, and I can cancel out all these L's now. Each term is a pi. Cancel that out. And I can cancel out this squared, cancel out this d here, and this squared. Okay, and then I'll go ahead and simplify that. And I'll get a negative dp dz okay, and this is going to equal 4 times shear stress divided by the diameter plus rho g sine theta. Okay, and then from here I'm going to define a new term. So this is the fanning friction factor. I'm going to define that as the shear stress divided by 1/2 the fluid density times the average velocity squared. So this is the definition of the fanning friction factor. There's also a thing called a Moody friction factor, and the only difference between the fanning and the Moody friction factor is that this turns into a 1/4, I believe, possibly a 1/8 for the Moody. I'm going to use the fanning friction factor for all my videos here. So this is the definition that we're going to use. So the next thing to do would be to just redefine the shear stress in terms of the fanning friction factor. So just solve this algebraically. So that's going to equal to 1/2 times the fanning friction factor times the fluid density multiplied by the velocity squared. Alright, and then I'm going to sub this into this expression right here. 1 second, let me scroll down. Okay, so I get a negative dp dz is equal to, so it'd be a 4 on 2, so that gives me 2 times fanning friction factor times the fluid density velocity squared over the pipe diameter, and I'm going to add to that a rho g sine theta. Okay, and the next thing that I want to do is just go ahead and separate and integrate this. So I'm going to get, it's pretty easy to separate and integrate. If we integrate this, we're just going to get the negative change in the pressure, and then we're going to multiply by the length of the pipe to each of these terms. So we get 2 times the fanning friction factor times the fluid density times the average velocity squared, and then we're going to get this L over D term here. And then to that I'm going to add a rho L G sine theta. Okay, and then what I want to do now is just go ahead and redefine my axis. If you can remember, the axis was defined like this, R and Z. So now I'm just going to redefine the axis like this. Call this just Y, and this will be my new Z. Sorry, I'm going to call this Z, and this will just be X. So X is the horizontal, Z is the vertical. By doing that new definition, I can now say that just delta Z is equal to L sine theta. And then if I take this expression, make this substitution, and divide out the fluid density to the left hand side, I'll end up with this final expression right here. So the negative change in pressure, over the length of the pipe divided by the fluid density is going to equal 2 times the fanning friction factor times the average fluid velocity squared, and then times this length over diameter of the pipe, and then I'm going to add to that a G delta Z. Okay, yeah, so that's a very useful derivation right here. We're going to use this quite a bit whenever we're trying to determine what the pressure drop across the piping system it will be. So this will be very useful. We can go on from here and just do one final derivation using a mechanical energy balance. So let me go ahead and scroll down. Okay, so I just copied and pasted mechanical energy balance here. And so the first term of the mechanical energy balance, the generalized Bernoulli equation here, is the kinetic energy term. And let me just go ahead and scroll back up to our original picture here. Alright, so this is the original picture. And then what I just want you to notice that the velocity of the fluid is not going to change. So at our point 1 here, the fluid velocity is going to remain constant all through here, the average fluid velocity. So I'm just bringing that up so that we can see why I'm crossing out this kinetic energy term in the mechanical energy balance here. One second. So we can cross out the kinetic energy term. We did have a change in elevation, so we're going to keep that. We do have a change in pressure, so we got to keep this potential fluid work term. And then we don't have any pumps or turbines, so we can cancel out the work term. And then the new addition is that we do have frictional effects because we're assuming that this length of pipe is significant and that shear stress is going to add up to having a significant effect over the length of the pipe. So we do need to keep this frictional term here. So now what we can do is we can use this relationship and plug it into here. So I'm going to say that my negative change in pressure over my fluid density is equal to, and I'm going to plug this in here for this term. Let's see here, what am I trying to say? So let me go ahead and back up. So this is the, if I take this term right here and I just move it over to the right hand side of this equation, that's what I'm going to do right now. So I'm going to say that that's equal to our frictional effects plus the potential energy. So that'll be your G delta Z. And then let me go ahead and solve for this F term right here. So F is equal to negative change in pressure over the fluid density minus the potential energy effects here. And you can see that if I plug this in, I'm going to get this entire expression will just basically get subbed right in here. And so I have a positive G delta Z and I have a negative G delta Z, so those are just going to cancel out. And I'm just going to say that my frictional effects are going to equal to 2 times the fanning friction factor times the average velocity squared times this L over D. So this is the other big derivation. It's very important. We're going to use this all the time when we're doing our pipe and plumbing problems. And then just the only little tweak that I'm going to make to this is just say that this is my L over D effective, because we can have effective lengths. So imagine if you have a pipe that's going straight down and then it makes a sharp 90-degree turn going to the right. So we're going to have quite a bit more frictional effects in this region right here, in this elbow, but we can characterize that by an effective length over diameter. So we can still use this derivation, and then we just have to take into account an effective length over diameter. And then there's tables in many fluid dynamics books that have, like, they'll give you an effective length for a 90-degree bend elbow. They'll give you an effective length for a sudden expansion. So if you're flowing from a narrow pipe and then it suddenly expands, they'll give you an effective length for that. And then conversely, if you're flowing from a wide pipe and then you suddenly contract, there's an effective length for that as well. And then there's effective lengths for gate valves, for elbows, for 45-degree bends. So basically, we're going to be able to use this derivation regardless of the geometry of our piping system. So this is going to come in a lot of handy. So that's pretty much it for this video, and I will see you in the next one when we start tackling some actual problems here.